Hi guys, today we will discuss about the topic binary search. So in DSA, why we will use binary search? So if we take an example, if, I'll be taking array which is having a sorted ascending order of elements. So you can see 1, 4, 9, 13, 17, 19. So here, let's say you have to find particular target in this array. Let us assume I want to find 9. So index of 9. I want to find the index of 9 here. So usually in a conventional approach or a brute force approach, if I want to find the index of 9, element 9 in this, the usual routine or brute approach, in that approach, what I'll do is the complexity will be O of n. So we will be looping through this entire array from starting to ending, and we will be doing an if case. So in that if case, if this particular 9 target is equal to array of I. So if that particular target is equating to this particular element, then we are returning the solution, returning that particular index. So in this particular scenario or in this particular approach, what we will be doing is the worst case, if we find number at the starting, the complexity will be 1, O of 1. So if we find number at the last, the worst case complexity will be O of n. Let's say if we have 10,000 numbers in that array. So if we have these 10,000 numbers in array, then complexity will be O of 10,000. Means whatever the size of this particular array, complexity will be O of that particular size, which is n. So this is a conventional approach. So here the time take to run the code and space will be more. So in order to avoid this, as this is a sorted order and it is in ascending order and the array is sorted, you can see 1, 4, 9, 13, 17, 19. So we will use binary search approach to this. So in binary search approach, the complexity will be O of log n, which is much lesser. Let's say I'll be taking few examples for this n, like 10, 10,000 and 1 lakh. Let's say 10 lakhs. So what log n means here is, log n means 1 here, log n means 10 here. Sorry, my bad. Log n means 100 here, and log n means 1000 here. So whenever the number n keeps on increasing, log n will be not rising that much as compared to the n, because log of n is a mathematical function which gives the results as 100 for 10,000 and 1000 for 10 lakhs. So in this fashion, so whenever the number is more, the given size of array is more, we can decrease the complexity much better and we can optimize the solution better. So let us see how we will apply the binary search. I'll just show the classic template. Mostly these classic template will go and apply for each and every binary search problem. So if we understood this particular classical template of binary search, then it would be very easy for us to apply in each and every binary search problem if we can crack that. So let me just clear this out. So the template, the usual code will be, or pseudocode, let's say, the pseudocode will be like this. We will be having an, let's say, array, this particular array, and we will be having, this is of type int array, and the target, in target to find, let us assume. So the first step will be, I'll be getting the size of this array, int n equal to array dot length. So this will be very useful, and I'll be determining two endpoints. One is at the start and one is at the end. So let us assume that int low, low will be the lowest index currently, will be 0, and high equal to n minus 1. High will be the largest index in that particular array. So what we will be doing is I'll be setting particular limits. So what I'm doing here is I'll be initially fixing these 2 points, like low here and high here. So using this low and high, I'll be finding the midpoint of that particular array. And using that particular midpoint, I'll be comparing that with our target. So whenever that particular value at that midpoint index is greater than target, means the value we get by using low and high, which is mid, the value at the mid index, if it is greater than our target, then we have to search on the left. In other case, if the value is lesser than the target, then we have to move on to the right. Means in the first case, if mid is less than target, what I will be doing in this situation is, if mid is less than target, then I will be checking in right part. Checking in right part means nothing but in the next iteration what I am doing is I am setting the new limits. Low equal to mid plus 1 and high will be obviously high. High remains untouched. This is the first case. So second case is if mid is greater than target, what I will be doing now is checking left. Okay, so checking left in the sense what I will be doing is I will leave the low untouched in setting the new limits, and high will be mid minus 1 because we have already checked mid. So in the first case the low will come here, let's say I'll be 1, 4, 9, 13, 17, 19. Let's say these indexes are 0, 1, 2, 3, 4, 5. So initially the low is 0. Let me draw here low, high and mid. So in these three things what will happen is initially we'll be setting low to 0 and high will be the index, highest index. So obviously 0 plus 5 by 2. Low is, mid is average of both low and high. So if I'll be calculating mid, which is equal to low plus high by 2. So now the mid will be 2 at starting. So what we will do now, at mid 2, I'll check value 9. Let us assume target also. Let us assume for the timing target is 13. So target is 13. So at second index the value is 9. So mid value is 9 and target is 13. So 9 is obviously less than 13. So we have to check the condition. If mid is less than target, we have to check right. So what we will do, this portion will just leave. We set our lower boundary to here. So firstly it is here, we'll be moving this to here because according to the condition. It is nothing but a basic sense where the order, in the ascending order, the number keeps on increasing from left to right. So whenever we find that mid number is less than whatever target we need, obviously the target is on the right. So that if the target is on the right, we just have to go to the right and we have to search there in that boundaries. So that's why high we just keep it as it is here at the index 5, but low we'll be keeping it to mid plus 1, which is 2 plus 1 equal to 3, and high remains stable. So 3 and 5, for 3 and 5 the average will be 4. So the new mid is 4 here. 17 is obviously greater than 13, so we just have hop onto the second condition. So in these new boundaries the mid is here, but the 17 is greater than whatever the target we need. So obviously we just have to check on the left. So what we will do, whenever we have to check on left, we just have to move that highest right higher boundary uh, to the left. Means in this 13, 17, 19, the mid is 17 and low is 13, high is 19. Means think in terms of indices. So as we saw that 17 is less than 13, we know that obviously it is on to the whatever number we need, it is onto the left of mid. So we'll be moving that high to that one left place. So what we will do, low is obviously 3 and high is mid minus 1, which is 4 minus 1 equal to 3. So the new mid is 3. So both low and high are present here, but the mid is, so you know that if the low and high is same, then the average will be also same. So now we will be checking 13 is equal to 13, means this 13 is the mid value, this 13 is our target. So whenever these two matches, we'll be returning the target. So what we'll be doing is we will be iterating until low is less than or equal to high. So we just keep a while condition so that it runs until this condition passes. Inside this condition we will do all this. First I'll check if array of first condition is, if I'll check array of mid is equal to target, I'll return that particular index. I mean index in the sense, in this case it is mid. Okay. Second case, we just have to apply this array of mid is less than target. Set new boundaries. I mean I'll simply write check right. So in that other case, else case, check left. So if this entire thing passes up and we come out of the while loop and we didn't find the correct target value, then we will be returning the -1 simply in case of we didn't find any value. So this is the classic template of a binary search. So you guys may ask, like binary search will be only applicable for the sorted array, but it's not. It will be applicable for the unsorted array as well. So the next one is, we'll check this particular same classic template example for the unsorted array, and we do the dry run here, so that we'll better get to know what exactly happening here and everything. So in order to do that, I'll just simply create one unsorted array example to the right of this. So let us keep this very simple. So I'll just create one array which is called A. A is having 5, 8, 4, 2, 1, 6, 7. Okay. So I'll write up the indices as well. So 0, 1, 2, 3, 4, 5, 6. So total here size will be 7, low is 0. We know that already. First we'll be keeping low at 0 and high at the highest index possible. High will be 6. We are not writing the code here, we just simply try to dry run this and check ourselves whether this particular binary search template is applying for the unsorted array or not. So if you can see here, I'll just set up a target. uh, Let us take 6 here. So target is 6. So obviously I'll just write low, high and mid. Okay, first low will be 0 and high will be 6, mid will be 3. Let us keep the value as well. So 3, the value is 2. Target also I'll keep just for comparison. 6. 2 is obviously less than 6. If 2 is less than 6, what we have to do? Uh, we have to go to the right, because target is more. We just have to shift to the right of this particular array. So if you want to shift to right, obviously low will be one step incremented to the mid value, which is 4 and 6. Now the mid is 5. So for the 5, the value is 6 in the array. 6 is equal to 6. So now we find out the value. So if I can simply take one more example, I mean the same example, but I'll just change the target value now. Randomly I'll just take 8 as a target now. So the target now becomes 8. It's always same. Target, the same condition, 2 is less than 8. So we just have to go to the right and check. Now you can see 2 is less than 8. So obviously we have to go to right. The same, these low, high and mid values doesn't change. Value also doesn't change because indexes and values were interlinked. So the target is 8. 6 is obviously less than 8. So once again what we have to do? We just have to shift to the right. So mid is 5. So 6. Mid is obviously 6. Value is 7. 7 is less than 8. So 7 is less than 8. What we have to do? We have to keep one step increment of low value, 6. So what happens here is 7 and 6. Low should be less than or equal to high. So whenever we define initially, low is here and high is here. So the low should not be interpassing the high and going to the right. So that's what happening here. Low value is 7, which is greater than 6, but it shouldn't be. So it is not satisfying this condition. So we will be returning -1. But if you can observe clearly, we have the target value 8 here. We have target value 8 here. But according to the classic template, we didn't find 8. We are returning the -1 according to the classic template. That means it is demonstrating that this classic binary search template will be applicable only for the sorted arrays. For unsorted, we don't use. For unsorted arrays, we don't use. This particular binary search won't be applicable. So that is it.